Hello again, this is Dr. James Camp from Lee College in Baytown, Texas, and this is my commentary on Chapter 3 of Big C++ by K. Horstmann. We're talking today about making decisions. First off, the if and else statements in C++ are used to implement a decision. Okay, so when a condition is fulfilled, or if a condition is fulfilled, one set of statements is executed. Otherwise, or else, another set of statements is executed. It is, in a sense, like a fork in the road. Ha 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 ha. Okay. No, that fork in the road. The if path leads you down one way, the else path leads you down another way. And maybe they come back together again on the far side and the program keeps going. Okay, so let's see what this looks like in C++ code. We have the word if, parentheses, and a condition. And then we have some curly braces defining a code block with statements to run when condition is true. Then we have the keyword else. No parentheses, no condition here. It's whatever the opposite of the initial condition is. These are the statements. And then there's another bit of curly braces defining a code block. These are the statements to run when condition is false. Okay, so let's take a simple example. If num%2 equals 0, that means number is evenly divisible by 2. Then we can see out num is even. Else, what are we going to do if else? Else means it's not evenly divisible by 2, so we're going to print num is odd. Okay, now your book has this kind of silly example of an elevator with a 13th floor problem. Okay, the building tenants are superstitious. Nobody wants to live on or have office space on the 13th floor. So one way to deal with this problem is to simply rename floor 13 to floor 14. We just skip 13 in our numbering system. But the elevator still needs to know that when you push the button for 14, you're actually going to the 13th floor. So try writing this yourself in pseudocode. Start a new page in your notebook. And then keep track of the C++ code on the same page. So our pseudocode looks sort of like this. If the user inputs 14 or higher, we're going to set the actual floor to 1 less. 14 becomes 13, 15 becomes 14, so forth and so on. Otherwise, else, we're going to use the supplied floor number. If they typed 12, then yeah, go to floor 12. If they type 7, we'll go to floor 7. So let's try translating this into a C++ if-else statement. Okay, we're going to read in the floor and define a variable called actual floor. That's where the elevator is going to go to. If floor is greater than 13, okay, notice we don't put a semicolon after the parentheses. Actual floor equals floor minus 1. So again, 14 becomes 13, 15 becomes 14, and so forth. Else, meaning they typed in a floor that was less than or equal to 13, the actual floor equals the floor. Okay. So if they typed in 7, we're going to go to the actual floor 7. Okay. There's another way to write this code, and that's to set actual floor to floor before we get into the loop, or before we get into the if statement. And then say if floor is greater than 13, we'll minus the actual floor. We'll decrement the actual floor. Okay. There's no else in this case because there's nothing to do if floor is less than 13. Actual floor was already set to floor. And this is what those two look like in flowchart form, you can see that the flow of the program hits this floor greater than 13 question mark. If it's true, that means we need to set floor -1. If it's false, that means we need to set actual floor equals floor because we're not greater than 13. And then, as I indicated with the fork in the road graphic that we saw a minute ago, once the if statement is over, flow of the program comes back together and the program can continue as one program. It is typically done in C++ programming that we line up braces under the I in if and then indent the code that goes inside those braces. There is an alternate style that's popular in some programming languages. It's not really proper C++ style for some reason, but is to put the opening brace at the end of the if statement. This saves one physical line of code, so if you are in the habit of printing out your code and want to make it a little more compact, you can do that. But the only reason I would ever use this style of code is that it helps remind you not to use a semicolon at the end of the if line, because you're ending the if line with the open curly instead of ending it with a semicolon. Generally, however, a lot of people find this style harder to read. It's not as easy to see which code the closing brace goes with, and the standard style in C++ then is to line your braces up vertically under the I, like we saw on the previous page. When the body of an if statement consists of a single statement, you don't actually need to use the braces. If you don't have a code block, if you just have one line of code, you could get away with just saying if floor greater than 13, actual floor minus. You can even put it all on one line if you really want to, though, again, that's considered kind of bad style. However, most people suggest that, especially beginner programmers, always include the braces. They make your code easier to read. And more importantly, you may find that you need to add a second statement later. And if you forget to put the braces on at that point, you have committed an error. If you put a second line of code in there without adding braces, then only the first line of code goes with the if statement. So it's better to have the braces all the time, and that's how our book is going to demonstrate code. Common errors. Putting a semicolon at the end of your if statement. We've mentioned this a couple of times so far in this lecture. Ending an if statement with a semicolon is not a syntax error, okay, in that the compiler will still compile your code. But if you're lucky, your programming language might pop up your compiler might pop up a warning indicating that semicolon maybe shouldn't be there. C++ interprets a semicolon at the end of an if statement as if you had written if floor greater than 13, semicolon. Okay, that's what we call a do nothing statement. It does not actually, it means if floor is greater than 13, do nothing. And then what happens to the curly braces and the actual floor minus, they become what's called an unattached code block, a code block that isn't part of an if statement or a while loop or any other thing. It's just there. C++ allows that. It allows you to put in code blocks that are just there without any reason to be there, and so the compiler won't complain about that either. But what's going to happen is actual floor minus minus is going to execute whether floor is greater than 13 or not, because it's no longer attached to the if statement. Okay. Block structured code can contain nested statements. That means you have one indented block inside another. And so the preferred style is to, again, line up your curly braces at each level of nesting and then indent each block within the curly braces by, say, 4 spaces, 3 spaces, I think is what they used in this example. How do you indent? Using the tab key is one way to get this indent, but remember that spaces and tabs are not equal. Okay, most development environments will automatically convert. When you hit the tab key, they'll automatically put in, say, 4 spaces. If you do your coding in Notepad or TextEdit, this will not happen. So if you mix doing some of your coding in, say, Windows Notepad and some of your coding in Visual Studio, you can have a mix of tabs and spaces in your code, and it's not going to make your code not compile, but it can end up making your code look awful when it displays on screen or when you try to print it. Especially if you open if you open it in, say, Word or something to try to format your code, Word is going to try to put your spaces to your tabs to every half-inch spacing, and it's going to look nasty. Also note that most modern IDEs will automatically indent your nested statements by, as they try to interpret the code you're writing as you write it. Sometimes they get it wrong. Often that's because you forgot something. Maybe you forgot to put a semicolon at the end of one line, and so it messes up the indentation of the next line. Or maybe you forgot to close one set of curly braces, and so that messes up your indentation. It's a good idea to fix the bad indentation before you forget what code goes with what, and it's a good idea to track down what it was that made the IDE get your indentation wrong in the first place, because 9 times out of 10 when that happens, it's because I forgot to include something in my code that I really should have included. Okay, let's consider this implementation of the elevator program. We've got it printing actual floor equals, or actual floor colon, and then the actual floor in both branches of the if statement, both the if and the else. That's kind of redundant. It's better to take the couts out of, since they're identical statements, pull them out of the if and else and replace them with one statement at the end that does the same thing. It saves you coding. It makes it easier to maintain the code. If you wanted to go back and change what the message was, you only have to do it once instead of having to do it in each branch of the if else. And it also saves a little bit of compile time and a little bit of computational time. Okay, C++ also has something called a conditional operator. Okay, you have to have a variable that's going to store the answer, though I guess you could use a cout there instead if you wanted. But typically you would put the answer variable equals, you type your condition and then a question mark, and then the value that's going to be assigned to answer if condition is true, and then a colon, and the value that's going to be assigned to condition to answer if condition is false. So this whole one-line statement can be read as if condition answer equals value 1, else answer equals value 2. It's a handy abbreviation. I use it sometimes. Actually, I use it quite frequently when I think to. But it's also a little bit harder to read than the if-else version. So if you find it hard to read or hard to code, you don't have to use it. It's just something there for programmer convenience. An example of how that works is shown at the bottom here. Instead of using the max function, which is built into the C++ standard library somewhere, I forget where, I think it's the algorithms header, you can just say larger equals val1 greater than val2, question mark. Okay, if val1 is greater, we'll pick val1, else we'll pick val2. And either way, we'll get the larger value stored in larger. The conditional operator is always equivalent to an if-else statement. So you can say actual floor equals floor greater 13, question mark, floor minus 1, colon, floor. And that's equivalent to this entire block of code that we've been writing this whole time to solve the elevator problem. So if you have a situation where you have an if and an else, and each one has exactly one statement that's doing an assignment statement, then you can use this conditional operator to line it out all on one line. If not, it's better to use the if-else in the standard if parentheses condition and so forth and so on. Okay. How do we build those conditions? Okay. We know that a condition goes inside the parentheses of the if, but how do we express that condition? Typically, we're going to use two values and what's called a relational operator. So for example, if A greater than B, greater than is called a relational operator. There are 6 relational operators in C++: greater, greater than or equal, less, less than or equal, double equals, which just is read as equal, and bang equals or not equals. Sometimes C++ programmers read that exclamation point as the word bang, which is just kind of fun to say, but really it should be read as not. So that is not equal. Here are some examples of these relational operators at work. 3 less than or equal to 4 is going to be true. 3 equals or less than 4 is putting the symbol backwards, and so that's not going to compile. 3 greater than 4 is going to be false. 4 less than 4 is going to be false, but 4 less than or equal to 4 is going to be true. Some more examples. 3 double equals 5 minus 2. Well, 5 minus 2 is 3, so that is true. 3 not equals 5 minus 1. Well, 5 minus 1 is 4, so 3 does not equal 4. That is true. 3 equals 6 over 2. That's an error. You're supposed to use the double equals to test for equality. And we'll talk about what happens if you use a single equals later. 1.0 over 3.0 equals 0.333333333. That's false because of rounding errors and problems in representing floating point numbers. And we'll talk about that again in a little bit. Okay. A brief aside about the equals equals operator. It's initially confusing to beginners because in C++, single equals already has a meaning. That is, it assigns values. If I say floor equals 13, I'm not asking is floor 13, I'm assigning the number 13 to the variable floor. If I want to test whether floor equals 13, I have to say floor equals 13. Okay. As a little side note, you can compare strings as well. If the user typed a choice in a menu program, and you want to know if the choice equals quit, you can say if choice double equals quit. Okay. A common error happens if you confuse single equals and double equals. Essentially, single equals is allowed in C++ because it was allowed in C. C did not make a distinction between Boolean values, true-false values, and any other integer value. So you could say if parens x equals 3, x is assigned the value 3. 3 is not 0, so it's true. And so if x equals 3 will always be true no matter what x was to start with. This is really, really confusing, and I'm not sure why C++ retained this coming from C, or why C had it in the first place. So the statement floor equals 13 has the value 13. Okay, 13 is not 0, so it is read as true. So if floor equals 13, we'll always assign 13 to floor and then always give that a true value. The compiler is not going to issue an error message there because it is legal C++. Though a good compiler or IDE might issue you a warning indicating that there's an assignment statement inside an if statement, and that, asking you if you really, really want to do that. Okay, so the moral of this whole story is remember to use equals equals inside a test for equality, and use single equals only when assigning values. Okay. I mentioned on the last page error messages versus warning messages. Okay, if a compiler issues an error, that means it cannot translate the program because there's something that doesn't follow legal C++ coding practices. You forgot a semicolon somewhere, or any number of other illegal things. You forgot to put the parentheses around your if statement, maybe. Warning messages are just advisories. The compiler will go ahead and translate the program, and it will let it run, but there's a good chance that the program isn't going to do what you meant it to. Okay, so check the warnings, and whenever possible, fix your code to eliminate the warnings, and that will make your life a lot happier as a programmer. Okay, so take a moment to write in your notes the difference between an equals and a double equals, what each one is used for, and the difference between an error and a warning in your compiler. All right, round-off errors. Floating point numbers have only a limited precision. Okay, calculations can introduce round-off errors so that if you are given r equals 2, the square root of r squared is not going to end up equaling 2 exactly. Okay, so how would this look in code? How would we test this? We say, well, r equals square root of 2.0. Then if r times r equals 2, and here we're using an integer value of 2, which I find interesting, then see out square root of 2 squared is 2. But that's not what it's going to print. It's going to go to the else statement, and it's going to print square root of 2 squared is not 2, but 2 point, a whole lot of zeros, and 44. The solution to round-off errors is something that engineers have known for a really long time, and that is you define a tolerance. In mathematics, we use the Greek letter epsilon for that, which just is a letter used to denote a very small quantity. I often use 1 times 10 to the negative 12 for my epsilon. Your book said it's a 10 to the negative 14. It doesn't really matter unless the extra 2 dots of precision, 2 decimal places of precision is important to your program. 1 equals negative 12 catches a few more values than 1 equals negative 14. Now we say r equals square root of 2.0 if absolute value of r times r minus 2 is less than epsilon. Okay, see what we did there? We turned r times r equals 2 into an expression that should yield 0 if everything is equal. So r times r minus 2 should be 0. If the absolute value of that is less than epsilon, then we print square root of 2 squared is approximately 2. And in fact, that's what would print if we ran this program. And you have to include the CMath header to get the square root and the absolute value function. Okay, what if we want to compare strings? Comparing strings uses what they call lexicographical order. Okay, remember our ASCII table? Okay, you'll note that numbers have smaller values than letters. Capital letters have smaller values than lowercase letters. But within each of those domains, the numbers have increasing value as the number increases. The letters have increasing value as you go through the alphabet. So when you compare two strings, you compare the first ASCII character of each word, then the second, and so on, until either one of them ends or you find the first letter pair that doesn't match. Okay, if one of the strings ends, the longer one, the one that keeps going, is considered the larger of the two. If you find a letter pair that doesn't match, the one with the greater ASCII value in that position is greater. Easier to give you an example than to just keep talking about this abstractly. So if we have the words czar, car, cart, and cat, believe it or not, czar sorts first, even though Z comes after A, because capital C has a lower ASCII value than lowercase c. Car and cart, cart is the longer of the two, so it sorts after car. Cat comes after cart because T is further down the alphabet than R. So I want you to write these words in your notes in lexicographical order, just as practice here. Pause the video for a moment and try to write these in proper lexicographical order. Okay, if you got Barkley and then Barry as the first two, then you remembered the point about the capital letters having lower ASCII values than lowercase letters. And then you would have BAR, and then barometer, and then BARRE. Okay. Sometimes you don't have a single pair of alternatives, if this, else that. Sometimes you have multiple alternatives. And in these cases, we have what's called an if-else chain, or an if-else-if chain. Consider, for example, the Richter scale for earthquakes. You have an earthquake Richter scale number come in. You want your program to print out which of these 4 outcomes, or the 5th outcome, no damage, which would be less than 4.5. Our flowchart would look like this. Okay. The code comes, the program comes in, it hits Richter greater than or equal to 8. If that's true, we print most structures fall, and then we loop on down and miss all the rest of the code. If that's false, however, we want to fall through to a question, is Richter greater than 7? If that's true, we'll go to many buildings destroyed, and then we'll loop on down to the end of the code. Okay, and you see it will keep falling through to the next if, and the next if, and the next if, until eventually, if all of these are false, we'll get to a place where we print no destruction of buildings, and then we rejoin the flow of the program at the end here. So let's see what this looks like in code. We say if Richter greater than or equal to 8.0, we'll see out most structures fall. Else if Richter greater than or equal to 7.0, many buildings destroyed. Else if Richter greater than or equal to 6.0, many buildings considerably damaged. And it keeps falling through. Note that if the first if is true, Richter greater than 8.0, it won't execute any of the remainder of that code because they all start with else. Okay. If, on the other hand, the first if fails, then the first else catches that, and we check the next if. Okay. So if I had a 5.5, I would fail on Richter greater than 8. Else if, I'd fail on Richter greater than 7. Else if, I'd fail on Richter greater than 6. Else if 5.5 is greater than 4.5, so that would catch my situation, and it would print damage to poorly constructed buildings. Then we hit an else. Well, I've already satisfied one of my ifs, so I'm going to skip the else and keep on going with the rest of the program. Okay. Because of this execution order, it's important to pay attention to the order in which you put the conditions. Let's say we accidentally wrote that program backwards. If I go through with my 5.5, well, if Richter greater than or equal to 4.5, we get the damage to poorly constructed buildings, everything's great. What if I go through with 7.5? If Richter greater than or equal to 4.5, well, 7.5 is greater than or equal to 4.5, so we'll print damage to poorly constructed buildings, and then we hit an else and an else and an else, so I'll never actually get to the point where Richter is greater than or equal to 7.0. So if you're going to use greater thans as your comparison, you have to start with the largest value first and work your way down. We could have done this and made it work in this order if we had used less thans instead. If Richter less than 4.5, see out no damage. Else if Richter less than 6.0, see out damage to poorly constructed buildings, and so forth and so on. Okay. Let's say we wanted to write code that takes a digit that someone types in and prints out the word that goes with that digit. Maybe it's for a text-to-speech recognizer or something. We can use an else, an if, and then an else if, and an else if, and an else if, and an else if. This code, there's nothing wrong with this code at all, but some people think it looks a little bit ugly. There is an alternative called a switch statement. Okay. Now note first that switch can only test int and char character types. Okay. It cannot test doubles because you can't get an exact match to a double. It can't test a string because you can't get an exact match to a string. Well, you can actually get an exact match to a string, but they just don't do it. So we switch on digit, and then it looks for the case that fits that digit. Okay, let's say I typed 5. It would switch on 5, so it would check this case, no, this case, no, this case, no, this case, no, this case, yes. So we go on ahead through, digit name equals 5, and then we hit the all-important keyword break, which skips down to the end of this switch structure. Otherwise, without the break, it would actually keep going with 6 and then 7 and then 8 and then 9, which is one of the inconvenient things about switch statements. Switch statements are really easy ways to code a menu-driven program. Let's say the user picks a choice from a menu of A, B, C, and Q for quit. Well, we can If they type A, we can subroutine A. If they type B, we can call subroutine B. If they choose C, we can call subroutine C. And in case Q, we just print a quit message, which is maybe something that says, thank you for using my program today, and then it quits nicely. If they didn't type any of those choices, then we print an error message indicating that they did not actually, that they chose an incorrect menu choice. Notice here that, let's say I type lowercase a, it's going to match case A, it's going to flow right on through case capital A, and it's going to do subroutine A, and then it's going to get to the break statement. Okay. What if I choose capital C? Well, it's going to come down here, skip right through C, but it's going to get caught by case capital C, and then it's going to play through that line of code until it hits the break. Okay. There's no reason that you have to put these all in one line of code. A case can have several lines of code. As long as it ends in a break, you're okay. Break tells C++ to skip down to the end of the switch statement. If the break is missing, execution falls through, we call it, to the next branch and the next branch and the next branch until it either hits a break or it hits the end of the switch. There are situations where this fall through behavior is useful, but it's not commonly useful, and it is a common cause of errors. So a lot of people have kind of a chip on their shoulder against the switch statement because of the problem with the break. If you forget the break statement, your program will compile, but it will execute unwanted code. In some other programming languages, that's not allowed, and it will actually catch those errors and make you fix them before you run your program. Okay. Last but not least, there is the idea of nested branches. Okay. In the United States, for example, different tax rates are used depending on marital status and income. Okay, married taxpayers add their income together and pay taxes on the total. So I earn slightly more than my wife. So we add our two incomes together, and if we make twice as much as a single person, then we go up a tax bracket or something like that. Within each group, whether you're single or married, you're then split into income brackets. You pay, this is a dramatic oversimplification of a federal tax rate schedule. This one says that for the first $32,000 you pay 10%, and then over that you pay $3,200 plus 25% of the amount over that. Common misconception is that tax brackets apply to your entire income. They don't. They only apply to each extra bit of income above the last tax bracket, which actually makes calculating your tax much more complicated. So this is what our flowchart for tax table decisions would look like. Notice that you have, you come into one decision, and the outcome from that takes you to another decision, regardless of which decision you made the first time. So this is what we call nested decision making. Okay, and this will come in here where you see if marital status equals S, then if, we have a nested if statement, and if inside another if income less than or equal to rate 1 single limit, then blah, else we get rate 1 single limit and then rate 2 times income minus the rate 1 single limit. And then we have the else from the first if has also an if and an else inside it. And that's the idea of these nested branches. A very useful technique for understanding whether a program works correctly is called hand tracing. You basically run the program in your head and you keep track of what's going on a sheet of paper. You can do this by following flowcharts, pseudocode, or C++ code. Okay, so looking at your pseudocode or your C++ code, you use a marker. Some people like a paper clip because you can just slide it down the piece of paper. You're going to execute the statements one statement at a time, and every time a variable changes value, you cross out the old value and write the new value down, and you can trace through. So tax 1 and tax 2 both start out as 0. We assume the user typed 80,000 for their income, and the user typed M for marital status. So we record those on our balance sheet here. If marital status is S, well, we're going to skip that whole section because marital status was not equal to S. And so we're going to take the else branch instead. Then if income is less than rate 1 married limit, well, what was that? Let's look it up. It was 64,000. Well, 80,000 is not less than or equal to 64,000, so that branch is skipped. And we're going to go to the else, and we're going to take this branch here. So rate 1 times rate 1 married limit is tax 1. That's 6,400. Rate 2 times the remaining income, income minus rate 1 married limit is 40,000. And then we calculate total tax is tax 1 plus tax 2, $10,400. All right. So now that you have a basic idea of how to write ifs and elses, here is a decision practice for you. The user is to input a date as a numerical month, 1 to 12, followed by a numerical day, 1 to 31. Your program does not have to decide whether the month actually has 31 days in it. You just go with it. Your program is to decide what season it is. Your program is to decide what season it is using the following algorithm. So if the month is less than or equal to 3, we set season equals winter. Okay, so season is going to be a string type variable. Else if the month is less than or equal to 6, season is spring, and so on. For less than or equal to 9 would be summer, less than or equal to 12 would be fall. If the month is divisible by 3, okay, so that's 3, 6, 9, and 12, right? But it's easier to just do divisible by 3. You know, take month percent 3 equals month percent 3 double equals 0. Then if the day is greater than or equal to 21, then we have to advance the season, okay? Because every third month, a new season starts on about the 21st of the month. So if season was set to winter, then we'll set season to spring. If season was set to spring, we'll set season to summer, and so forth for summer and fall. Okay, so work on that in your all too abundant spare time, and let me know how it goes. Until next time, good luck and happy programming.